Go back and look at these one more time.
I feel way too much.
Yeah, I think the number I get is 8 meters squared. Someone else got 4. Somewhere in that range. Someone got 1 too, so somewhere in the single digits of meters squared per hectare. The literature values 2.
Is it a little? But I have.
So I know only like a couple minutes, but why would you use for the second one? Why do you use the delta H and not delta G?
For the second,
Yeah, like when you're doing it for the when it's asking you to compare for the steam forming.
oh, because the entropy change is minuscule, you're going from gas to gas. What the H is doing really matter.
Okay.
Delta S is very small, so you can just do delta G of delta S or delta H there. I'm going from 2 moles of gas to 2 moles of gas, the delta S is minuscule.
That makes sense.
Yeah, it doesn't matter.
Okay.
You could certainly do delta G, that's fine. Delta G doesn't really tell you though, because what delta G tells you is that delta G is negative, but if it's an endothermic reaction, it's got to pull heat in from somewhere. And the fact of the matter is that if it pulls heat in from somewhere at 450, you've got to have a heating element that's at 450. So you got to apply energy to keep the air at 450. The system can be endothermic at that temperature. So the heat that's required for the reaction ultimately tells you how much energy your heater needs to run because you need to maintain your temperature at 800 Celsius. Right? So imagine you didn't have that heater. Well, then if you didn't have that heater, then you'd be at 298. So it doesn't work. So you got to bring in energy to keep the system running at 800. It's constantly absorbing that energy. So you got to keep supplying that energy into the environment to maintain that 800 Celsius.
Okay.
So the enthalpy is really the important number. If delta G is negative, that means that it's entropically favorable. It will give you some energy back as entropy change,
I totally.
but that's a
did-
very small number.
what I did wrong was definitely I used the wrong temperature.
And the fact of the matter is industrially, they're not going to use that entropy that comes, the extra heat that comes out of that reaction from Gibbs if it's negative. The
Mhm.
energy the system gets back, it's just going to be thrown away.
Yeah.
Because it's not worth, it's expensive to reproduce that into work. Take heat and convert it into work, you have to have an entire new pump system or some sort of turbine to convert that heat that it generates. No one's gonna do that. They're just gonna heat a giant coil to 800 C and maintain it at 800 C. And so therefore, the enthalpy is the thing that ultimately determines your energy use because that's how much energy the heater has to supply to maintain that temperature for the reactor. Yeah, I'll put it this way, the heat, yeah, the energy that you're supplying to it is not to drive the reaction forward, it's to maintain the conditions of the reaction. And the reaction's endothermic, so if you imagine you initially had your reactor at 800 C and then you turn the heater off and you let it start reacting, it's endothermic, so it's going to cool the air down because they're going to absorb heat from the air. And eventually your temperature is going to drop because it's absorbed all that heat for the reaction. So you got to put in more energy to heat it back up.
Yeah.
And that is the enthalpy. You have to compensate for the enthalpy. I have to use the restroom really quickly. Just give me a second. Blame it on Monica for getting me to talk. And making me lose my place here. All right. Talk amongst yourselves for just a minute. I'll be right back. And we'll get started. And let me share my screen. That's okay.
Have you tried to do 1.5 yet? I finished 1.4 last night, so no. That's a figure it out. Can you let me know? I'm like close, but my number's off and I cannot figure out why. I see. You have my number, right?
Yes, because I needed to get you your details from Quant for
Yeah,
your glassware for uncertainty.
well, throwback.
Because I was working the next day.
Yeah, that sounds about right.
Okay, sorry about that. So what I want to start with today, we're going to kind of, from here on out, just kind of grind through different types of reactions to talk about their kinetics. So we're going to start simple and work our way up to more complex things as we go. This is perhaps my favorite lecture of the semester. I'm going to teach you a little bit of a kinetic story. A story, a theory, if you will, a model for understanding a certain type of reaction that is very counterintuitive. And it actually teaches a really important lesson about reactions. And I think it's a really interesting story. But before we get to that, I want to kind of set the stage for kind of our discussion for the next, actually probably until the last week of classes. Let me say this really quickly. So what I want to talk about today is we've been talking about rate constants and the activation energies and things. I want to kind of change perspectives and think about kinetics from this is a really big word. It's the only word I can think of. Is from a phenomenological point of view. The idea that kinetics is something that you observe, and we need to have a model to understand our observations. So instead of thinking about building things from the ground up, where we think about things microscopically and understand how kinetics and reactions occur microscopically, let's come up with macroscopic models, things that we can do in the lab to explain how reactions work, right? Describe the mechanism in the kinetics. And so the word that a philosopher or a rather pretentious scientist like myself would use is what's called phenomena. It's a phenomenological rate or kinetics. The idea is that we observe a phenomenon, something that occurs, right? And we're going to describe our theory to understand our observations. Right? That's compared to what's called an ontological theory. An ontological theory is one where we understand the root cause, the fundamental nature of something that exists. I'm not going to do that yet. We'll come back to that kind of ontological concept of how do reaction kinetics form for microscopic behavior. Come back to that question. But rather, I want to think about interpreting kinetics from the point of view of an experiment. Right? We see things forming and depleting. Right, we don't really understand what's going on underneath the hood. It's too much. But maybe we can come up with an idea of what's going underneath the hood by interpreting our experimental results. All right, so this is what I would call phenomenological kinetics, which is the idea of, let me just kind of say this is about the idea of modeling reaction mechanisms through interpretation of experimental behavior or experimental observations. All right. You might say, okay, well, that kind of sounds like an empirical theory, and it is an empirical theory, but the idea is that we can use empiricism and understanding to kind of really dig out the underlying behavior. Rather, I'm trying to talk about a model that allows us to describe the behavior we observe mathematically. Right, so instead of thinking of why, it's just how do we talk about reactions when we observe them in an experiment. And this is just a really, really fancy way for me to say that we're going to discuss the idea of reaction rate laws. And we're going to kind of go through a series of common types of rate laws. We'll classify these rate laws and talk about their math and their physics and their chemistry, different applications of each kind. And we kind of glanced at this idea before. The idea is that a rate law for a reaction where we have reactants A1, A2 to AN with stoichiometric coefficients V1, V2 to Vn. reacting or equilibrating with products called V prime 1 B1 plus V2 prime B2 to Vn prime Bn. Right, so we have n, or maybe we have m products. We'll write this as m instead of n. We might have more products or less products than we have reactants, but you know, we could have, it could just be A to B, it could be A, B, C, D to E, F, G, H, you know, any number of products with stoichiometric coefficients. And we can write what's called a reaction rate wall. Which says that well, we can write it two different ways. We can think of, for instance, the time derivative of the formation of one of our products. And it's going to have some associated rate to it, Kr, right? The observed rate that we have. And it's going to be a product of the concentrations of our reactants to some power. And we talked a little bit about these powers. All right, this, yeah, A sub K is said. Or N sub N, yeah, N sub N. And it depends, so the values of N1, N2, blah, 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 these are called the reaction order. And these specify the number of mole equivalents of the reactant that are involved in the so-called, what's called the rate determining step. Of the reaction. Right, so I've given a couple terms here that I haven't defined yet. The reaction order has something to do with, for instance, if this were A to B, and we did the kinetics and we saw that the rate of B's formation is proportional to the concentration of A squared, that would mean two molecules of A are coming together in the transition state. Okay, so it tells you how many mole equivalents are coming in at the transition state. Because of it at the transition state, that does not mean that the system is, that these molecules interact corresponding to their stoichiometry. For instance, you could, let me give you an example. Let me give you a good example of this. So the claim I'm going to make here is that the order numbers, the order parameters, are not necessarily equal to the stoichiometric coefficients. I stated this last time, right? Because the stoichiometric coefficients tell you about this total stoichiometry of the reaction, but they tell you nothing about what's happening at the transition state, and that's what matters. Let me give you an example of what I mean by that. Transition state structure. Determines the reaction. Let me give you an example of this. It's okay if I go to the next page, because so far. Yell at me if you want me to go back. So let's go back to our SN1 reaction. So a molecule that readily undergoes SN1 is T-butyl bromide. Again, we're just going to do the same conditions that we had in our previous problem when we discussed SN. Just going to simplify this. So T-butyl alcohol, bromide ions. Actually, if I don't know if you guys know, TP-butyl alcohol is a really wonderful, a really cool solvent. It freezes just under room temperature. So at 20 C, it has beautiful crystals that form in the liquid. It's really nice, it's really pretty. It's one of the few small alcohols that have a freezing point around room temperature. So let's think a little bit about this reaction. So the way this reaction works is like this. I'm going to write a reaction coordinate diagram for this reaction. So we'll put it on we'll put this reaction on a coordinate system. Let me just redo that. Coordinate system. And this first line here is our reactants. And the way this reaction works is quite interesting. Right, so it turns out that we have some intermediate. Let me put the final state here. So the final state is lower energies, delta G less than 0. This is CH3 TP-butyl alcohol plus bromide ion. And there's this intermediate state, right? We saw that the intermediate for this reaction is this CH3 C cation plus bromide ion. Let me move this over so I have a little space. So we have this intermediate system where we have the system ionized into two parts. Well, it turns out that this, in fact, is an intermediate. This is a stable species. So this is not actually turns out this is not actually a transition state, but rather the system is stabilized here. Like so. Right, and there's actually a small transition state right here, where this corresponds to where the CH3C is being partially ionized and the bromine is being partially ionized. And this system is stabilized by the solvent. So somewhere in here, there is some solvent molecule, some number of solvent molecules that are interacting with the system, right? In fact, this SN1 reaction has to be in what's called a polar and a protic solvent. It needs to be polar so it supports that ionization, right? So for instance, this works very poorly in dichloromethane. Or hexanes, right? A very nonpolar solvent, but it works great in DMSO or dimethylcetamide or acetonitrile or methanol or ethanol, right? These are polar and protic solvents. You need to stabilize that transit. You need to stabilize the ion complex that forms. And so if you have a material that's not very polar, it's not going to be very favorable. But you also should consider now that there is also another transition state here, right, where the formation of the hydroxyl system, right, this would be CH3 C plus partial positive charge connecting to an OH with a partial negative charge, right? These are transition states, if you will. Right, it costs some energy to do that, and then the system reacts down like this. Right, but again, this needs to be stabilized by a solvent as well. Right, so the question, of course, is what is the order of this reaction? Well, the fact of the matter is that the only thing that's really slowing down here, that's slowing the system down, right? The solvent is, imagine the solvent is completely ubiquitous, right? There's tons of solvent in excess, right? So the solvent ions, right? Imagine if I change, well, let's think about it this way, right? So what kind of species can contribute to our rate, right? So what are our possible, this is probably a better way to think about it, possible rate contributing species. All right, well, one obviously is the solvent. Right, maybe the solvent contributes to the rate, right? Because the solvent stabilizes the ions. So maybe the solvent will change things, but the solvent doesn't change the kinetics, right? Because the solvent is in excess. And from the point of view of the reaction, having twice as many solvent molecules makes no difference. It just makes it harder to find things, right? Solvent has no appreciable contribution to the rate because of it being in excess. All right, so even though the solvent is interacting with the system, again, remember what's happening with the rate law is we're asking how fast does the rate increase? How fast does the reaction speed increase as we double or triple or have the concentration of a material? And the solvent, of course, is in excess. There's so many solvent molecules. On average, there might be 10 per unit cation, maybe more, hundreds. Right? If you add another one, it makes no difference at all. Right? So the solvent doesn't contribute to the kinetics appreciably. In fact, what the solvent does contributes to delta G of the reaction, but not to the kinetics. The idea is if you have a solvent that doesn't promote the formation of ions, then your delta G of this reaction is going to be pretty non-favorable, right? The reaction doesn't want to go forward. So it contributes energetically to the system, but it doesn't contribute to the kinetics. Right? The solvent will tell you how favorable this reaction mechanism is. Some solvents are favorable, some are not. And that just is basically a question about delta G, not about the kinetics necessarily. Okay? When we double the concentration of the solvent, we're not actually changing anything about the rate because it's in excess. Right, so it's not the solvent. And then we can also think about the OH ions, the nucleophile. Bless you. But this does not matter because the formation, the reaction of the cation with OH is energetically favorable and in polar solvents barrierless. Right, so even though I wrote a little hump here for the addition of OH, in fact, that hump isn't real. If it's in a solvent that promotes the formation of ions, adding a negative ion to a positive ion is always favorable. Right, it's downhill. Delta H is less than 0 is exothermic. More than happy to do that. Right, so in reality, in a favorable condition, the reaction diagram actually just goes straight downhill. Like this instead. So that's not a real transition state. So the only thing that's left, right, the only thing that can contribute now is the reactant itself. Right? Ultimately, the most expensive part of this reaction is the ionization. Right? Because CH3, 3, Br, sorry, I forgot the carbon, to T-butyl cation plus Br minus has a delta G greater than 0. It's the only thing that's costly in here, right? So the thing that ultimately bottlenecks our reaction is not the solvent. Solvent's just there. It's not the OH, because by the time the OH is ready to react, the system is prepared and ready to go. The moment that OH sees that cation, it just connects right in. So the only thing that can be left is the concentration or the reactant itself. Right? The energetically costly part of this step process is the breaking of that carbon-bromine bond catalytically into plus and minus. Right, so this step right here, I'm going to do it in a big square here. Right, this step right here in blue is the real transition state of the process. Right, the reaction is not. The reaction transition state is not where this OH comes in and attacks this methyl group like it is in SN2. Remember, in SN2, the transition state is where that OH is coming in and a BR is leaving. This happens in 2 steps. The BR leaves, and then eventually the OH comes in and reacts. And so the transition state for this process is just the breaking of the carbon-bromine bond. So this is the transition state here. And it's the thing that determines the kinetics. Right? And because it determines the kinetics, we call this the rate determining step. And it says that that means therefore the only species that contributes appreciably to the rate of this reaction is the reagent itself. And there's only 1 mole equivalent of reagent per step, right? Because it's only 1 molecule. So therefore, that means by definition that the formations of our products, the reaction law for this rate, for this reaction, right, which is the time derivative of the product, is equal to some rate, K, R, times, bless you again, the concentration of our starting material only. And it's to the first power because only 1 molecule is involved in the transition state. Right? And this is true. This is why it's called an SN1 reaction, because it's a nucleophilic substitution that is first order. It has only, its order parameter is 1 for 1 species. So this is what we call a first order reaction. Okay. So for SN2, right, remember SN2, the transition state involves the bromine and the reagent. Sorry, the oxygen, the OH and the reagent, right? They all come together into 1 species, right? So that's SN2, that's a second order product in the second order reaction, and its rate is again the reagent, right? The reagent's involved in that transition state, and so is the nucleophile, OH. So for SN2, the kinetics would be Kr with the concentration of the reagent times the concentration of OH, the nucleophile, because the nucleophile is involved in the transition state. I'll write that down. Well, actually, we'll come back to it later. All right, so we'll look at these second order reactions next week. I want to stick to first order reactions today. I want to teach you something very interesting about first order reactions. All right, so again, SN1 has nothing to do with how much nucleophile you have in there. You can double the amount of OH you have in there, and the reaction conditions do not change. Reaction rate does not change. But if you double the number of reagents that you have, obviously you form products twice as fast because you have twice as many reagents in there. It forms twice as quickly. What does change when you change the solvent? Right? The idea is that if you change the solvent to something that's not polar, K will change. Right? The value of the rate constant will change. The idea is that the energetics of all the transition states and the products and the reactants and all that are changing together, they're all changing together collectively. So the mechanism does not change. So regardless of the solvent, these are always the kinetics. This is always the rate law, regardless of the kinetics resonant one. But Kr may be really, really slow if you say do this in hexane instead of in ethanol. So it ultimately determines the rate constant, which is related to the energetics. It doesn't change the mechanism. So let's look very carefully at these first order reactions today. This is the kinetics of one molecule reacting on its own to form products. I want you to pay attention and keep in mind that lying underneath this discussion, and it says first order, there's always solvent molecules interacting here. There's always these little these little observers, if you will, that are hanging out and doing stuff, but they don't necessarily appreciably affect the kinetics, but they're always there. Solvents are always there, and solvents are important, right? We're going to look at that situation at the logical extreme, where you have you only have a product molecule and no solvent in there, and we'll see that the kinetics are slightly different. The solvent plays an important role. It's hard to explain exactly how it plays that role until you see the theory for it. But we'll see that the solvent does play a role in the limit where the solvent is no longer in excess. So when we bring the solvent back, the same being stoichiometric with your material, there it's not really a solvent anymore. Now it's a reagent, if you will. And the kinetics for this process changes. Solvent becomes important. All right, we'll see that today. Okay. So let's just do some very, very simple some discussion about first order reactions. Really, really simple math. I just want to blast through this really quickly. It's not super important. I really want to get to the conceptual meat of all this. So we're looking at reactions A to P. Okay. And we showed that the rate of depletion of A, which is equal to the rate of formation of P, is equal to minus Kr times the concentration of A to the first half. All right, so what we'll do is we'll like we did when we talked about equilibrium, what we're going to do, we have a differential equation here. Right, we have an equation that says the derivative of A with respect to time is equal to a function of A. So let's solve for A and get a function for the time dependence of A. Right, this is just saying that we have a function A of t whose slope is proportional to the value of A. All right, so we'll do that solution. So we start with really, really simple math. We start with this expression. All right, and I'm going to rearrange this. So now I have dA over the concentration of A, which is equal to minus Kr times dt. Right, I've separated the two differentials together and combined like terms. So I have a t on this side and A on this side. This is just the most basic differential equation in the world, separable differential equation. I can integrate both sides of this and use the fundamental theorem of calculus to calculate the value of A at any temperature T. If I integrate both sides of this. So I'm going to integrate the left side with the lower bound is going to be the initial concentration of A to the final concentration of A at some time. And I'm going to change the interior to a dummy variable, so not to confuse. So we have this integral on the left-hand side, and we're going to integrate minus Kr dt, t is time here, and we're going to integrate from the time where the concentration is initial, which is 0, to the final concentration at time t. And I'm going to dummy integrate dt prime, not to confuse our variables here. Right, so I'm going to integrate from t equals 0, the concentration at t equals 0 is A naught, to some time t where the concentration is A. This is a really, really easy integral to do. So the right-hand side is just the integral of dt. So this is minus kr times t minus 0, which again is just minus krt. And the left-hand side is basically dx over x. That's the log of x. So we have the log of a at some temperature time t minus the log of the initial concentration. Like that. So I can write that the log of the concentration of A at any time t is equal to minus kRt plus the log of the initial concentration. And now I just take the exponent of both sides. Take e to both sides. Right. So on the left-hand side, we get e to the log. That just gives me the argument of the log. A of t. So the time A, the concentration of A is a function of time. It's going to be e to the rest of that. And just with a little bit of math, that's going to be the initial concentration minus e times e to the minus kRt. So this is what's called the integrated rate law. For a first order reaction. Again, very, very simple, right? This is, if you guys remember maybe from intro chem, when you talk about like isotopic reactivity and half-lives and stuff, an isotope decaying is a first order reaction, right? There's one element, one atom emitting and breaking apart. In a fission process to form, right? And you have a half-life associated with that. And again, that just comes from this math, just first order kinetics, it's exponential decay. And so we can rewrite this because what we're really interested in is the products as a function of time. And that's really easy to solve for. It looks like this. I'll plot these for you. So if we want to plot the depletion of our products with respect to time, we start at A naught and we exponentially decay. And if we look at the plot for the product concentration as a function of time, again, it starts at 0, right? Because there's no products at the beginning, and it's 1 minus e to the t. The asymptote is A naught, right? Because you convert all of your A into P. And it looks kind of like this. So this is a classic first order reaction. What this tells us though, which is nice, is that if you take the log of the concentration as a function of time, it's a linear function in T. And this is how we often identify, first order reactions is we plot when we plot time versus the log of the concentration of the material. We start at the log of A naught and we get a linear decrease like that, where the slope is equal to minus KR. All right, we'll look at first order reactions in lab next semester. Look at second order as well, right? But they're very, very straightforward, right? Super easy to do if you can measure your products or your reactants and you measure their concentration as a function of time. You take the log of the concentration of the products or the reactants, you get a straight line. Okay. For only first order reactions give you this behavior. First order always means log of A versus time is linear. When we get to second order reactions where two molecules come together, you get a different behavior. I get a different graph. So this is how we always identify empirically or phenomenologically that we have a first order reaction, that the log of the concentration is linear in time. Any questions? Should be pretty straightforward. Most people have seen a first order reaction in their life. Again, this is just radio dating, carbon dating. We often learn about this when it comes to radioisotopes. Typically, the first order reaction you learn is uranium-235 decaying or some other radioactive material. It has this decay, this half-life, and every first order reaction has a half-life. Let's go look at the half-life really quickly. So let's calculate the half-life for first order reaction. So we often define the half-life, depending on who you ask, t to the tau 1/2. Sometimes if you're into video games, lambda 1/2. If you ever played the game Half-Life, there's a reason why they call it lambda. That's the other way that engineers often call it. And this is defined as the time it takes to deplete. Sorry, that's supposed to be half the starting material. So we can just simplify this really quickly. We can just do this really easily. Let's assume that the initial concentrations of our product are 1. And that would mean then that our half-life concentration is 1/2. So we're going to get an equation that looks like 1/2 is equal to E to the minus KR times tau 1/2. All right, well, that's a really easy equation to solve for. And it says that tau 1/2, which is the half-life, is equal to log of 2 divided by the rate. Right, and this is roughly equal to, I'll just write it here, 0.693 divided by the rate. Okay, so what this means, again, it's not very interesting, right? It's just a simple algebraic number. But when we look at bimolecular reaction, we have two things coming together. The half-life is quite a bit different. And the most important thing to note here is that this half-life is completely independent of concentration. It's a fixed number. It's independent of conditions. Well, it's only independent on conditions except for temperature. Right? Because Kr is proportional to E to the minus 1 over temperature, right? So Kr changes with temperature, so the half-life will change with T. But otherwise it's completely something that's set, it's unique to that mechanism. Right? Never changes. Right, so that's really helpful, right? If you have a first order reaction, you don't ever have, if you want to curious about the kinetics, you never have to worry about your initial concentration, because the amount of time it takes for you to deplete half that initial concentration is fixed at fixed temperature. Really, really nice. We're going to find that in a second order reaction, where you have two molecules coming together, that the half-life depends on the concentration of one of them. And maybe that makes a little bit of sense, right? If the reaction depends on two bodies coming together, the half-life should probably depend on the number of targets one molecule has to hit. But maybe that's not so surprising. But it's nice to know that, again, half-lives are basically, or first order reactions are basically concentration independent. Concentration independent. Now let's see how well this works in theory. Or in practice. So let's look at a very simple reaction. Maybe this is something we'll look at a little more carefully soon, but I'm just going to give you kind of a result. So there's a really, really interesting process where HCN, sorry, I have the errors wrong. Arrow is wrong, it's the wrong way. Product reactant favored. Well, isomerize with HNC. This is in the gas phase. All right, so here's a really classic, actually, it's one of the most classic first order reactions. HNC, HNC. So there's an equilibrium between these two. And so you would say, okay, well, I'm curious about, let's say I create, let's do it the backwards. So let's say I create HNC from a reaction process. So the initial concentration of HNC is not equal to 0. And let's assume that HCN concentration at initial time is equal to 0. Okay. So there are some reactions. I could show you an example of one from my work where we can generate HNC and you can actually watch it convert over time to HCN. It does it kind of spontaneously. And that's kinetics. All right, so we would ask, okay, what kinetics would we see? Right, let's just remind you that in a gas phase, typically when we do things in a gas phase, we have some other material in there, like a solvent. We typically do it in, say, helium. Typically, we have some sort of material. If these are really, so if you want to have system to react and you want it to kind of flow like a fluid in the gas phase, you typically don't have enough pressure of your reactants materials to do that. So we tend to fill our reactor with some sort of inert gas like helium. It's like a solvent for the gas phase, right? So sometimes we would do this reaction, we would pressurize it, say, in 1 bar of helium. So I'll say that this is in helium in 1 bar. Or some pressure. Okay, so there's some helium solvent, right? We call this a buffer gas. Which is like an inert gas phase solvent that gives our reactor more fluid-like properties. So heat can transfer more effectively and things like that. All right, so this is for heat transfer. ETC. Maybe we have a heater, right? Imagine we have a tube that we're making HNC in, and we got to heat our material up, right? And to transfer that heat into the vacuum, you've got to have some pressure, right? You have to have molecules in that to transfer that heat from the walls. So we're going to use that helium kind of as a heat transfer agent to our reactants, okay? They're not reactive, right? Helium's atoms are just dumb balls that carry heat, right? They don't do anything else. Right? We call that a buffer gas, right? It's just kind of like a solvent, the spectator. And then you go do this experiment, you ask the question, well, what kind of reaction order do we get? Okay, so we go to high pressure. Let's say greater than 1 bar, kind of on the order of 1 bar. And we measure the formation of HCN, right, because HNC is being formed first. And we find that this forms exactly the way we expect. Forms with a little bit of HNC. First order. I'm going to bring this over to the next, actually, I'm going to copy all this over the next page so I have some room. So you don't have to do anything. Just let me zoom out a bit. Okay. Very simple. Exactly what you would expect. Guess what happens as you turn the pressure down? So now we go to intermediate pressure. Right, so think about that. Maybe this is between 1 millibar and 1 bar. What we observe, interestingly, right? If it was first order reaction, if this is a first order reaction, we won't see any changes to our kinetics, right? I mean, as agents, assuming that the only thing that we're changing, imagine we make the same amount of H and C every time, right? So the initial concentration of H and C is fixed. And so what we're just changing is the amount of helium in the system. Okay, we're pressurizing the system of helium or depressurizing. Okay, so the same amount of H and C gets made every time. So we're intermediate pressure of helium, and we measure the rate of formation. And what we observe, right, given this note, if we make the same amount of H and C every time, the rate of formation HCN is fixed at constant temperature. It should not depend on pressure because we're making the same amount of H and C. The number it is, H and C is fixed. The only thing that's changing is the total pressure of the system with the helium. So we would expect at intermediate pressure, we'd get the same kinetics. But it turns out that that's not what you see. What you find out is that as you start to get to lower and lower pressure, again, it's still dependent on the number of H and C molecules you have. But what you find is that it starts to become second order. To some coefficient that's a function of the pressure. So this is some number in a P that is between 1 and 0. So as you start to lower the pressure of helium in your system, the kinetics start to be dependent on the concentration of helium. Now, it's not a perfect one first order, but as you start to get the lower and lower pressure, N of P starts to increase towards 1. It starts to become increasingly more and more important. So what we observe actually in the system, I don't know exactly what the curve looks like, but I can kind of guess, is that if we plot P versus N of P, and again, it could be between 0 and 1. Again, it's 0 at high pressure. And it increases and then flattens out. It has a logistic progression like this, low pressure. So it starts 0. Basically, the helium does not interact with the kinetics at all. And then there's this critical pressure where the amount of helium that you put in starts to matter. And then it levels off to the point where it becomes first order in helium. So now the solvent's starting to interact with the system. Very strange. And then what if we do it neat? Right? No helium. Right? So let's assume that our pressure of H and C is maybe on the order of a microbar. And what do we observe here? What you find, and this has been shown many times, is that it's second order. Sorry, I have that wrong. H and C, sorry. It's second order in H and C. So what we have is the pressure dependence, right? At high pressure, the system's first order, exactly like we would expect in gas in the liquid phase, right? Just like SN1, very normal. And then as you start to lower the pressure of the system, basically making your solvent more and more dilute, the system becomes second order. Bizarre, isn't it? Let's try to understand why this is. This is a completely general result. This is completely general for first order reactions.
You're saying that happens for every.
Yes, yes, that there is this limit. You bring the concentration of your material low enough, and I'll explain why this is in a second. We'll go through the mechanism of this. That all first order reactions ultimately become second order reactions. First order reactions are only first order reactions in a specific set of situations. But if you took a single, imagine you have a reactor. Imagine you have a reactor that has one H and C molecule in it. You okay back there?
Yeah, somebody's out there, I'm just like, I'm asking, after just like a calculator in the car.
Oh, okay, awesome. So if it were a true first order reaction, you have one molecule in your reactor. That will convert to HCN spontaneously at any time, right? Eventually it'll react at first order, right? It only depends on the molecule. They're truly first order. If you do this reaction, if you do this system, if you do this, I don't know if anyone's ever done this before, but the idea, hypothetically, if you have actually one H and C molecule in a reactor, only one molecule, it will never turn into HCN. You need at least two H and C molecules for one of them to turn into HCN. It is required to be a second order reaction at the limit of minimal number of molecules. Low concentration, very, very low concentration is the limit of a first order reaction to second order. It's only at the limit of high concentration that it becomes first order, right? So a single H and C molecule will never turn into HCN by HCN by itself, never. Never, well, it might, but we're talking about winning the Powerball here. I can show you some data at 1 microbar that H and C turns into HCN within about a millisecond. All right, so if you're at pressure of 1 microbar, H and C will convert to HCN in about 1 microsecond, 1 millisecond. Right? If you're at nanobars, that kinetics is basically infinite. It never reacts. H and C never reacts. All right, it constantly stays H and C. It needs to have another body nearby to react. Right? So let me talk about that mechanism, why that is. All right, this is what's called the Lindemann-Hinshelwood mechanism. And I would love to tell you the story of this. Maybe I'll tell you next class, talk a little bit more about it. This is a result because people realized that first order reactions can't be first order at low pressure. All right, there were some experimental results that were discovered in the early 1900s that made people realize that first order reactions aren't truly first order at low pressure, low concentrations. They're second order. So someone had to come up with a mechanism for why that is. And Lindemann and Hinshelwood were the men that did that in the 1920s and the 1930s. And I'll show you some, if we have some time, if not tomorrow, I'll show you some experimental results that kind of satisfy their approximation. Okay, so we're going to look at A to P. All right, and so here's what the Lindemann-Hinshelwood mechanism is. It's a couple of different steps. The first step is collisional excitation of A to some energized form of A. All right, so we got like a cold molecule of A just hanging out. and it's gonna hit something, maybe a wall, maybe another molecule, and it's gonna energize itself. Okay, so this requires two bodies, right? So we're gonna do this in the absence of a solvent or a gas, so this is neat. No buffer gas. All right, but the argument of buffer gas is exactly the same. So this fundamental first mechanism step looks like A colliding with A to form an excited A and a non-excited A, right? This is what's called an inelastic collision. Right? One molecule of A is going to give another molecule of A some energy through a collision. All right, so what is the rate law for this simple step? Well, the process dA prime dA star dt is going to be some rate, we'll call it K1, I'll call it Ka, times the concentration of A squared. Right, you need two bodies to do this. All right, what can A star do now? Right, now we got to think, now we have this new transient species A star. What can A star do? Well, A star can collide with A to lose energy. Right, that's just the reverse reaction that we just wrote down. And that would be A star plus A goes to 2A. Right, and of course that would be some other reaction K, we'll call it KB, some other rate of collision. Actually, no, let me call it Ka prime, because it's the same process as before, times the concentration of A star and the concentration of A. Okay. Meanwhile, A star can also lose energy by forming P. Right, so that would look like A star goes to P, and the rate law for A star, we'll call this KB, and it's truly first order, right? It only depends on the number of excited A molecules you have. So if I were to draw a reaction mechanism for this, or reaction coordinate diagram, we have A here, and let's say we have some transition state, we may not, and then we go to products, like this. The idea is that this system, it gets excited collisionally by Ka to some new state, which I'll just kind of draw like this, which is A star. Right? It can react using Ka prime to go backwards, or it can react at a different rate to form P. Right, so in fact, this is what we really need to think about, is that there are two different types of A. There are regular A's, and there are these energized A's that are sitting above the barrier, okay, that are caused by collisions or some sort of energetic process that gives them energy. Could be a laser, for instance. But here we're just considering gas, right? It's just a natural, there's no lasers in here. We just have one molecule. If we have molecules of A hanging out doing things by themselves. Okay, so let's try to calculate the total rate for the formation of P, or the total rate of the formation of A. Right? We have three different processes that are competing. Are we good to go to the next page? Are we all good? So yell at me. I'm going to, I'll new page, and I'll kind of move it over like this. All right, so our total rate for the formation of A star, right, this is the species that we really care about, right? It's the thing that actually reacts to form P in this mechanism. is going to be equal to, this is the total rate, it's going to be equal to Ka times the concentration of A squared minus Ka prime, right? This is the depletion rate. Which is to go backwards, which is a function of A prime and A. And then there's the reaction rate to form P, KBA. All right, so I'll just remind you, this is collisional activation. This is collisional deactivation. And this is reaction. Okay. So again, there's not much I can do with this right now, but let's make an important assumption. The fact of the matter is that when I go look at this reaction phenomenologically, right, I go sit with my spectrometer and I look at A and I look at P with my spectrometer and monitor as a function of time, I'm going to see a signal for A that depletes and a signal for P that rises, right? There is going to be no signal for A prime. A prime is a transient species. The idea is that A collides with A sufficiently enough to create A prime, and then A prime is just going to do something immediately. Either it's going to go backwards or it's going to go forwards. So let's make the assumption that A prime is just an intermediate. So now what we'll do is we'll assume A prime is a short-lived intermediate. Or that the idea is that Ka prime and Ka are very fast. Right, the idea is that the A's are colliding with each other constantly, exciting, de-exciting, colliding, exciting, de-exciting, exciting, de-exciting. Okay. And so that means that A prime is only, every time it gets created, it basically gets instantly destroyed. Okay. So what that means is that over time, A gets created as fast as it gets destroyed. Okay, and so if we think about the concentration, just very simply, if we think about the concentration of A prime as a function of time, it's oscillating very rapidly. Being created and destroyed, created and destroyed. Right, so if I average over this measurement, right, if I think what is the average measurement, right, the average value of A star, it's right, the average concentration of A star is a fixed number, fixed in time. So therefore, we can say that the time derivative of its concentration is equal to 0, right? It's basically being created and destroyed as fast as possible. So if we average for a long time over multiple steps, over multiple reactions and multiple passes, that the concentration of A prime doesn't really change very much. It's just 0. It's flat. Okay. This is what's called the steady state approximation. Right? It's the idea that this reaction may have some sort of intermediates that don't exist for a very long time. They're created readily, but they're also destroyed readily. And so we can always assume, we can make an approximation that their time derivative, their concentration is equal to 0. They get created just as fast as they get destroyed. Right? So the whole thing basically cancels itself out. All right, so then we go up to this total rate here, right? We can write this equal to 0. Right, the total rate of A prime is 0. Really, really nice. All right, so what can I do here? Well, now I have this expression here that I can solve for A prime, the concentration of A prime, right? So now I can solve for the steady state concentration of my intermediate. So what I'm going to do, I'm going to just do that. So we'll solve for steady state concentration of an intermediate. And I'm not going to do that algebra, it's just a little bit of simple algebra, just to save some time. And so it says that the steady state of concentration of A prime is Ka times the concentration A squared times Ka Kb plus Ka prime times the concentration of A. Okay. So what do we use this for? Well, remember that the rate law for the product that we wrote is Kb times the concentration of A star. All right, so now we can write, right now we can eliminate the concentration of A star by this expression for it, which is just dependent on the things that we can measure, right? These are all things that we can measure. Can't measure this, but if we assume that it's steady state, we can represent its concentration by a bunch of things that we can measure. And then we can measure, we can relate the formation of the product to that set of parameters that we can measure. Right? We can get rid of that A star now. We don't even have to think about it anymore. We can get rid of the intermediate. And so we're left with Kb Ka A squared over Kb plus Ka prime A. All right, so this is what our rate law actually looks like. Right, so we have in the numerator something that looks second order. Right, we have this is the activation rate, the collision activation rate times the product formation rate, that's some new rate here that's product, times the concentration of A squared. And then we've got this denominator that has something to do with the collisional deactivation. It's called Ka prime A, right? So we're gonna have to think a little bit about what this looks like at different values of these different parameters. It's gonna be different limiting cases. Awesome, we got 5 minutes, perfect timing. And we'll follow this up next class with a bit more. So let me take this expression here and just do one more page. We'll finish this up. Oops, sorry, that's the wrong box. One more page. All right, so we have this new expression now. And again, this is for the reaction. Let's just remind ourselves this is for the reaction of A equilibrating with A star, which equilibrates with P. All right, so let's look at some limiting cases for this. All right, so let's do high pressure. The high pressure limit. Okay, so this means that collisions between A's occur frequently. Right, collisions are occurring constantly. Okay, so that means that therefore that the rate of A prime and A is much faster than the rate of A prime P. right? A's are just constantly smacking into each other, right? They barely have any time to do anything else but to hit each other, right? High pressure. Right, so what does that mean? Well, that means therefore that this rate is again Ka prime A star A is much, much greater than Kb times A prime. And if we divide both sides by A prime, we get that Ka prime times A is much greater than Kb. Okay. Look at our denominator now. We can make an assumption here. Right? If Ka times A, Ka prime times A prime is a really, really big number, we can neglect Kb. Right? Imagine this number is 10 million and this is 1. What's the difference between 10 million and 10 million 1? Nothing. Right? Who cares? So we can get rid of this Kb in this approximation. And that would tell us now that dP dt effectively looks like Kb Ka times A squared over Ka prime A. Right? Doing a little bit of algebra, I'm going to put these three parameters together into a single one called K observed, to some effective rate constant. And what does this look like? It looks like K observed times A. So we have first order. Right? So in the limit of high collisions, the systems are constantly smacking into each other. The A's are constantly smacking into each other and equilibrating with each other. The reaction reduces to first order exactly like we expect. Let's consider the opposite. Right? Low pressure. Right? It's the opposite case. Here, Kb is much faster than Ka prime. Times the concentration of A, which basically means no collisions or rare collisions. And this kind of means that A prime is long lasting. And therefore we get dP dt is equal to Ka, Kb times A squared. And the Ka prime A goes away because it's small over Kb. And we're left with Ka times A squared. Second order. So in a first order reaction where one molecule reacts to form another molecule, it's actually effectively a second order process. You need a collision partner. The fact of the matter is that at high pressure, and by high pressure I mean liquids, condensed phase, fluids, where collisions are occurring rapidly. So that's just in a liquid, right? Collisions in a liquid occur on the order of femtoseconds or picoseconds, really, really fast. They're constantly colliding with each other. First order reactions look like first order reactions. Because that collisional activation, deactivation is just occurring rapidly. So we can cancel it out. Doesn't matter. It doesn't contribute to the result because it's always happening. But in the limit where you only have one molecule or a very small number of molecules and there's very rare collisions, like in a vacuum or in space, unimolecular reactions are second order because you need a body to transfer energy to. You have to have another body, right, to activate the complex, to get it up above the transition state. And then that body needs to lose that energy somehow. And the only way it's going to lose that energy is by collision. So what this means, in fact, is that at the limit, at the microscopic limit, a unimolecular reaction, which means it involves one molecule, or let's just say a first order, is a two-body process. You need a collision partner. So even though the kinetics are only dependent on one body, effectively at high pressure, in reality, dynamically, you need another body to transfer energy to through a collision. Right? So a unimolecular reaction, which is a reaction occurring on one molecule alone, a decomposition or an isomerization, like we described HCN and HNC, requires another body for it to occur. Right? It's a matter of how often it sees that other body describes the kinetics of it. Okay. So I'm out of time. We'll look at an experimental result of this on Monday, right? And then we'll continue on because this kind of puts us into two-body interactions, right? We got to start thinking about two things colliding, right? So this gives us a nice place to start there. We'll start looking at bimolecular interactions and reactions next class.
Can I ask a question?
Yes, of course.
So I was kind of confused though, because like, it makes sense, but why, like, does the second body, does it need to necessarily be like the solvent?
Well, it can be anything.
Okay.
So for instance, when we talk about how in helium atoms are actually what are causing the energy change. So
why
in
do you
HNC
need a
to
solvent?
what?
Why do you actually need a solvent?
For the buff, for like a buffer gas? What? Well, so think about it this way, like, it's hard to explain, but imagine it's a flow issue. So if you have a very, very dilute gas, right? And the distance between, the idea is that your molecules are floating randomly. They need to be close enough to something so that while they're during the resonance time, they have a chance to collide with something. Think of it like laminar flow, right? You want to have, like, imagine you have a flow reactor where molecules are flowing from one side to the other and you're reacting them as they move through.
So when we were describing like the
When they're-
A colliding with A to
Yeah.
ignite A, it could be A with the one of the
Helium.
inert gas.
It could be a helium atom, yeah, or it could be with the walls of the reactor too.
Okay.
Any sort of body that will absorb that energy. But the reason why we use a buffer gas is because if you have, say if you put a microbar of HCN in there, it doesn't flow. Because in order for something to flow, all the velocity components of all the atoms and molecules need to be moving in the same direction. So if they're not colliding each other, they don't move, so they just sit there. It's called molecular flow regime.
So then.
So in a laminar flow, like an atmospheric flow, one bar flow, everything is colliding and moving in the same direction as each other. And so we tend to use helium to create it so that it acts like a normal flow.
So then how come that
It's easier to control.
like at like I guess like at low pressures, then I don't like the math makes sense, but I don't fully understand why like because in order for it to transition from the excited state to like the product,
Yeah.
it's like what
It needs to
occurred
collide.
that's happening.
Well, it could collide with something else, but it can also emit a photon and cool as well. There's other ways to react. So let me explain the answer to that question. It turns out that, so your question is, so you understand that you need a collision to go from here to here. But your question is, when you get here, how does this happen?
Yeah.
There's many ways for that to happen. So one is that it could collide again. Another thing is that it can emit a photon to relax energy. Imagine an excited state.
Yeah.
The photon to relax, the ground state. It can also, there's also radiationless transitions in molecules too. Things that change the energy of the system without emitting a photon. It's called intermolecular vibrational redistribution. There's many different ways, especially in complex molecules, for a system to remove. So the idea is that A prime becomes P prime here. And the kinetics of P prime to P, there's lots of different ways for that to occur.
Okay,
And it's a molecule dependent reason.
I'll not overthink it then.
Don't overthink it.
All right, thank you.
Yeah. Kayla, question?
Hi, could you take a peek at my?
Yes, of course. Yeah, Chris came by. Hopefully you guys.
We keep missing each other, so we're barely collaborating.
Uh-huh.
We're trying. I got this from this. Does this look kind of right?
22 point, that looks really close.
Okay.
It looks a little large, but you're getting there. It's definitely a positive number.
Well, this is just the,
That's just for H2.
yeah.
Yeah, I know. So you're doing the formation info piece.
I didn't know how to word NIST.
Okay.
Stuck on that for a while, but I just figured it out.
Yeah, you got it. You just take these numbers and then just,
Okay.
plug them in and go.
No, I think Chris has the other part.
Yeah,
figured out.
let me check this number for you really quickly. I think that's pretty close. This is wrong homework. I'm off, I have I have half the size of that. Yeah, isn't that annoying?
So I.
Let me see what you did.
I typed it in.
Well, that wouldn't
correctly.
explain why that would be caused. Let me look at your coefficients really quickly compared to mine. 3H, so you have 33, 11,363, 11,432, 2,773. Minus 158, minus 9.918 and 0. That does all look okay. H, so right, you have 0 for the enthalpy at 298. That's correct. So let me 723. So I have 12 kilojoules. Why is this different than what you have?
I divided by 1,000 for the temperature.
Yeah, I did too.
Okay.
Yeah, no, that's exactly right. No, the number is reasonable. If you didn't divide it, it would be a massive number, right? Because you'd be like 723 squared. So it's a
Yeah.
really big number. So you did that right. C4. Are there any negative signs? Just on E, right? So this is negative. Okay, so E is negative, so that should be a positive number. You are doing everything correct here.
You think I just have a math there?
You may have a negative sign that should be a positive sign or something like that.
Okay,
But your number's in the right vicinity, but I mean, everything looks exactly the same as what you have here, and I have 12.4.
okay.
So you're close.
Somewhere.
You might have written a 2 instead of a 1 there. That could be it.
Maybe.
But anyway, good luck. But you look like you're on the right track.
Thank you so much.
You're welcome. Hi, Charlie. What's up?
Carol's in the middle of using the bathroom, so I would ask this question for her.
Okay.
If she's waitlisted for right now for PCAM, but the e-pay statement is available, if her father pays.
I don't know the answer to that question. I think so.
I'm pretty sure.
This happens all the time.
So the thing is she.
Don't
must
they
have
charge
known-
you with under the assumption that you're going to have all those full credits? Is that how that
I
works?
don't know, maybe. Well, I was gonna say, she just paid the difference. And that's what I told her. And she was like, that's what I said to my dad, but he lets me ask. I'm just gonna say.
Yeah,
yes.
I would ask the registrar that. I really don't know the answer, but just say yes, yes. And let me tell you, this must happen, this happens to everybody all the time. So this can't be the only class that's waitlisted right now.
Probably not.
So this must occur.
I mean.
And I figure the registrar has some action for it.
They're changing the PCAM stuff now, so like forensic science doesn't have to take PCAM 1. It's quant and then PCAM 2.
They haven't voted on that yet.
I think it's confirmed for this year's freshmen, from what I've heard. But this year's freshmen, they don't have to take a quant.
Well, Valentin said they were not gonna vote on that until they told me.
Oh, interesting.
So either someone's not telling me the truth, or they're not telling me the truth.
The answer's a tell.
No, that's not PCAM 1 that they're losing, it's PCAM 2 that they're losing.
I thought it was PCAM 1.
No,
and
PCAM
quant.
2.
Oh, interesting.
Because to be honest with you, thermo and kinetics is probably more useful for you guys than quantum. But Valentin wanted to keep PCAM 2 because of spectroscopy.
Yeah,
But the argument, because Calc 3, you don't really need Calc 3 for this class, you need it for the other class.
For PCAM 2.
Yeah, because we do integrals and spherical coordinates and
that's
stuff.
what I was wondering, because when I heard about it, that they were dropping PCAM